In this video we'll look at the remainder and factor theorems. So we've already done work with long division of polynomials. So here we have a dividend being divided by a divisor of x plus 3. We end up with a quotient here and the remainder down here. We've seen that we can express p of x, therefore, which is the dividend here, in terms of the quotient multiplied by the divisor, then plus the remainder. So if we were to consider where x is equal to negative 3, if we were to substitute negative 3 into our polynomial function here, we'd end up with 2 times by 9, which is 18. Take away 7 times by negative 3, which is plus 21. We've got a plus 24 there. That's all in brackets. Multiplied by, I've got negative 3 plus 3, which is in fact 0, minus 73. So what happens is all of this becomes 0, and we're left with an answer of negative 73, which turns out to be the same as my remainder down here. So that's what we'd expect based on that calculation. But if we were to in fact substitute negative 3 into the original polynomial, so this polynomial once again here, then we end up with 2 times by negative 3 cubed, which is 2 times by negative 27, minus 9. I've got a minus 9 again, and a minus 1. So we end up with negative 44, and then minus 19, and that will in fact combine to give us negative 73. The same result we had here and the same result we had there. So it looks like if we want to work out the remainder when dividing by x plus 3, if we substitute negative 3 into our polynomial, then we actually end up with the same value rather than doing the long division. So, in general terms, if we have a polynomial divided by a divisor, we can express the polynomial in terms of the divisor multiplied by a quotient with a remainder. If we were to allow x to equal a, which is in fact the 0 from the divisor, then we end up with 0 times by whatever q of a is, plus the remainder. That becomes 0. We're left with just the remainder. So p of a gives us the remainder, and that is known as the remainder theorem. So if I were to divide p of x by my divisor here of x take 2 using long division, it'll take us a while to do that. So if I do all that there, I start 2 terms in, and I have x squared timesing by x makes x cubed minus 2x squared. Subtract that there, I end up with a negative x squared, bring down the plus 6x. Now I multiply x by negative x to make negative x squared, and I've got a plus 2x. Subtract all that there, I end up with 6 take 2, which is 4x, bring down the negative 4, times the x by positive 4, and I'll get 4x take 8. Then if I subtract, I end up with negative 4 plus 8, which is 4. So my remainder is 4. Now, if I were to do that using the remainder theorem, which essentially says if I divide by x take 2, then p of 2 should give me that same value. So let's work out p of 2. So p of 2 is going to equal, I've got my 2 cubed, which is 8, then my 3 times by 4, then 6 times by 2, minus the 4. These two cancel out. I'm left with the same value of 4. So p of 2 works out the remainder much more quickly. Alright, so there's the remainder theorem there. If I divide a polynomial by x take a, Then the 0 from here, which makes the divisor equal to 0, is a. If I worked out p of a, I actually get the remainder. So for this one here, if I worked out p of 3, that would give me the remainder. And for this one down here, if I worked out p of negative 2, that would give me my remainder. Now, that ties into the factor theorem. So what do you get as a remainder when you have a factor? If I've got 20 divided by 10, 10 being a factor, I end up with 2. There is no remainder. 5 is a factor of 20. I end up with 4, no remainder. Over here, 7 into 20 goes 7 2s are 14. With 6 left over, we do have a remainder. So we get a 0 remainder as we have here and as we have here if in fact we divide by a factor. So, right, so when p of x is divided by x take a and the remainder is 0, then once again working out the remainder, we work out p of a. If we get 0, that means our divisor x take a is in fact a factor. So this example here, if I worked out p of negative 3, I'll get 9 take 15 plus 6, which in fact gives me 0. And therefore I know that x plus 3 is going to be a factor. Likewise, if I worked out p of negative 2, I'm going to get negative 2 squared, which is 4, and then 5 times negative 2 is take 10 plus 6. Once again, that gives me 0. Therefore, I know that x plus 2 is a factor. Okay, and you know that anyway because that quadratic there would factorise into x plus 3 times by x plus 2 using the sum and product technique. Alright, so in this question here, if you wanted to work out the remainder, if I divide by x take 2, then the remainder will in fact be p of 2. So substitute into my polynomial and you'll get 8, take away 5 times 4, minus 2 plus 4. So we end up with, what's that, 12 take 22. So we end up with negative 10. Okay, and this one, find the value of k such that the remainder is 5 when dividing by x take 1. So the remainder when dividing by x take 1 is p of 1. And therefore, in this case, p of 1, which is the remainder, has to equal 5. So, working out p of 1, we substitute 1 into the polynomial. We'll get 1 minus 1 plus 2 plus k. So therefore we end up with 2 plus k equals 5, and therefore k must equal 3. Okay, deciding if you have a factor, then once again a factor should give a remainder of 0. So if I worked out p of negative 1, that will work out the remainder when dividing by x plus 1. I will get 1 plus 1 take 3 take 6, which is going to be 2 take 9, which is not equal to 0. So therefore x plus 1 is not a factor. As opposed to x take 2, if I worked out p of 2, I will get 8 plus 4 take 12 take 6. So I end up with, that's not going to be a factor either. I'm going to get to negative 6 as the result. So that is also not a factor. We need to get 0. Okay, some tricks for finding factors. All the possible rational solutions are factors of the constant divided by factors of the leading coefficient. So in this case, leading coefficient being 1 means that all the possible rational solutions will be either 1, 2, 3, or 6. They are factors of 6, but plus or minus those factors. So if I wanted to work out what my factors are, if I worked out p of 1, p of negative 1, then one of those, or the 2, 3, 6, should give us a 0, and therefore we have a factor. So likewise here, factors of the 12 would be the 1, 2, 3, 4, 6, and 12, plus or minus those. They are all the possible values you would try to get a 0 remainder. Another trick to look out for is if you add the coefficients of your polynomial, and if they add to give a value of 0, then that means 1 is a solution. So in this case, add up those coefficients. I got 1 minus 2 plus 2 minus 1, which in fact gives me 0. So in fact, p of 1 would give me 1 minus 2 plus 2 minus 1. Over here, I've got 2, take 2 would cancel out. So I've got 1 plus 1 is 3, take 3 gives me 0. So I know that p of 1 is going to equal 0 in this one here.